I'm Mike from MotoIQ, and because a lot of you guys wanted to see how we actually assemble an engine, we're going to do a video on assembling a Honda B18C. Howard Watanabe is going to help us. He's our master tech that builds all our motors. I've known him my whole adult life. I used to work with him at TRD. Howard's the one that taught me how to build engines like 41 or 2 years ago, and he really is a master at his trade. And so take it away, Howard.
You have to talk now, Howie. Say something for like 5 minutes.
We're just joking. A lot of this stuff carries over to like just about any engine, but you know, if there's any Honda specific things, if I remember, I'll point it out. But it's all basically the same. The first thing you do is get your engine properly machined, and we've talked about that in all of our videos. When you get the engine back from the machine shop, never take the machine shop's word for that. So you want to measure everything. So you want to measure your bores, your main bores, everything, and you need to get all this stuff so you can kind of set your clearances. So we're going to start with the main clearances. So Howard here, he's already kind of pre-assembled the bearing shells for the mains in the block, and you want to torque it down to the actual torque that you're going to use. This is very important. So Howard, go ahead and torque it down. Using the right torque is important because you want to get the bearing crush and all the block distortion and everything the same as when the engine's going to be operational. So, you know, Howard's here torquing everything down. He'll do it in several steps. He's going to go in an X pattern from the inside out. This is basic like what you do with any engine, but it's good practice. So you can see how he's going in multiple steps. He's going in an X pattern from the inside out, and we're using a snap-on torque wrench. It's important to have a very accurate torque wrench. So, you know, we'd like to use these electronic ones from a reputable manufacturer, and we calibrate it periodically, like maybe once a year or something. And so as it's coming up to torque, it's beeping to know we're at the set torque. So there we go, we're at torque. Block is all stressed and distorted just like it will be in operation. Next thing we're going to do is measure the bearing bores. So what we do at the same time we machine the block is that every reciprocating part of the engine we precision balance. So we balance everything to within 1 gram and dynamically balance the crank, the rods, the pistons, the pins, and everything. You know, that way everything's the same weight. And then now we're going to set our oil clearances, and we'll talk about that now. So a lot of people use plastic gauge when they're doing this kind of stuff, but plastic gauge is a no-no. You know, it's probably better than nothing, but a lot of people depend on it, even pros. We don't agree with that because it's really important to get your bearing clearances exactly where you want them, especially with aluminum blocks. Aluminum blocks grow with heat, and they're kind of unforgiving. You get your clearances on the loose side, the engine will have trouble making oil pressure, you know, especially your hot idling oil pressure. So we always use like a bore gauge and a micrometer. That way, you know, we can measure it within, you know, 10,000ths of an inch. So the first thing we're going to do is get our bearing bores. So we use a micrometer to set the bore gauge, and then we also measure the crank, and we use a micrometer for that. So you never want to use calipers. A lot of guys will use calipers, but they're only accurate to about the thousandths of an inch, and we want to go to the 10,000ths of an inch. So the micrometer is the way to go. No calipers, no plastic gauge. And so Howard's going to measure the journal diameter in 3 areas just to make sure, we don't have any weird tapered or out of round. You can see him doing it right there. And what he'll do is write down all the diameters for each journal. For the mains, he'll also do the rods. That's for when we set the rod bearing clearance. So now Howard will know the crank diameter. So now he's going to use that to set the bore gauge so he can actually measure the journal size in the block. So what Howard's doing is that he's setting the bore gauge to each journal diameter. So when he measures the bore in the block, it'll give the exact clearance. Now in an aluminum block, if you're running a conventional oiling system, like based on the stock oil pump, like a wet sump, we like to set the clearances on the tight side of OEM. This will keep you to where you have really good hot idle oil pressure. Otherwise, the engine may have trouble generating good oil pressure. If it's on the big side of stock clearance, especially if it's a turbo motor and you're bleeding off some of the oil pressure, you might not hardly have any hot idle oil pressure at all. We like to set like tight. Now, if it's a full race motor, really big horsepower, like what we'd probably recommend is you run a dry sump. And if you're getting to like over 800 horsepower, for instance, like a 1,000 horsepower B series motor, we'd probably set the clearances a little bit on the wide side, and the dry sump can make up for that, that pressure bleed off, because basically with the dry sump you can make it so it has almost any volume you want when you work with your dry sump manufacturer. And the bigger clearance will kind of make up for the crank flexing and the block flexing when you're making really big power numbers. But for most of you, it's probably better to set your clearances on the tighter side of OEM. Now, like once we've measured everything, confirmed what clearances we have, if we want to adjust it, what we typically do is most performance bearings come in 3 sizes, so we'll have all 3 sizes, and we can actually match each journal on the crank for each bore in the block. So we can mix and match bearing shells or run different sizes and get the exact clearance we want. So for the rod, it's the same thing. We're going to get the rod, put the bearing shells in there, then we're going to tighten them down. Now, a lot of guys will just go to torque, but when you have performance rods and performance rod bolts, you should always torque to stretch. So in your instructions for the rods, you'll have a torque and you'll have a stretch specification. Now, measuring how much the bolts stretch when you torque them down is way more accurate than just going off the torque. So we use this ARP dial indicator to measure stretch. ARP sells it. It's low profile. It's easy to get into weird places of your engine. So Howard's going to check the length of the bolt with like no torque on it at all. And then he's going to torque it down to a little bit below the spec and then do the final bit with stretch. Now these boost line rods are pretty good. Like the torque and the stretch are pretty close together. Typically with other rods, the torque doesn't stretch the rod bolts all the way, so we have to go a little bit past the recommended torque to get the stretch right. But really, stretch is the safe way to tighten your rod bolts. It's more accurate than torque. When you're measuring the rod and main cap torque, it's really important to properly lubricate the bolts. Now we use ARP lubricant, and that's probably the only thing you should really use. It's designed to help you get more accurate readings. So what we do is apply the lubricant to the threads before we do any torque or stretch measurements. So here we go, we're at the low end of the torque spec. Now Howard's going to measure the stretch. And are we dead nuts?
Yes.
Oh wow, okay.
5,000.
So we're right on the correct torque spec without it messing around. Now what we've noticed is that boost line rods are really good in this respect, and that's not typical. Generally we have to tie in a little bit more, and we kind of go by angular torque to get the last little bit of stretch, but that's not bad. So now Howard's going to measure the rod journal diameter on the crank, and like the main, he's going to measure it in a few places to make sure everything's round and we don't have taper wear. Once he sets the nominal diameter, he'll set the bore gauge to that, and we'll get the oil clearance. So set the 0 to the bore gauge, to the journal diameter, and now measure the big end bore diameter with the bearing in there, and you get your rod clearance. So like the main clearance, we could use different bearing sizes, mix and match the shells, get the clearance exactly where we want. So we do that for every single journal in both the block and all the rods, and that way we have consistent clearance across the board and the exact clearance we want. So we have good oil control, good hot idling oil pressure, and we don't overtax your lubrication system, and everything's nice. And like I said, aluminum blocks are a little bit less forgiving to fudging around than like your old iron blocks, so it's a very important step. The next thing you want to measure is your piston to wall clearance. So that's obviously the clearance between the cylinder wall and your piston skirt. So the first thing we're going to do is measure the piston skirt. Now every piston manufacturer has a measurement of where you are supposed to check the skirt diameter. It'll be in the instructions of your piston. It's usually like something like 10 millimeters up from the bottom, but look at your instructions. They'll always give the place where you're supposed to measure. So Howard measured the piston diameter in the right place. Now he's setting the bore gauge, and he'll go over and measure the bore, and then that will give you the piston to wall clearance. Now he's going to move the bore gauge up and down the bore and measure the piston to wall clearance in several places to make sure the machine shop didn't mess up and put a taper. So he's going to measure probably in 3 places up and down the bore. And he's going to measure in different quadrants too to make sure the bore is pretty round. Now, if you bored your block and honed it with a torque plate, it's not going to be perfectly concentric. It's going to be off a little bit, but I guess you could put the torque plate on and do it, or we have experience, so we kind of know how much distortion to expect, and we can have a good guess at this. But you always want to measure your bores, because you wouldn't believe how often the machine shop can mess up. I mean, we use the best machine shops around, so we don't have problems, but we've seen plenty of other engines where this has been botched. A lot of engines we have to fix that other people built. This is a very common problem. So it's always important to check this dimension and make sure everything's good. It's kind of the difference between a lot of local shops. They don't use this kind of care. They just get everything back from the machine shop, slap the engine together, or they'll do a cursory check with some plastic gauge. Usually don't check the bores. But if you have an engine that rattles, burns oil, smokes, wears out real quick, generally it's because of poor machining and poor assembly. So we check all the bores. What Howard will do, um, he'll match up a piston to a bore, and we'll know pretty much that the clearance is right. So the next thing we'll do is set the ring end gaps. So a very important step when building an engine is to set your ring end gaps. Now we order our piston rings slightly oversized, and we hand fit each gap for each ring, for each piston and each bore. So what Howard's doing is putting the ring down the bore, then he's going to square it up in the bore with the piston, make sure it's perfectly centered correctly. Now he's going to measure the ring end gap with a feeler gauge. And since we use a slightly oversized ring, it'll be tighter than spec. The ring end gap spec is always in your piston instructions. So when selecting a ring end gap, we will go to what the piston manufacturer recommends. Now if it's a street engine, we'll do it on maybe the tight end of the spec, especially if it's naturally aspirated. If it's a race naturally aspirated engine, we'll go a little looser. And if it's a turbo, nitrous, or blower motor, we'll go to the wider end of the spec. This is because these motors can run hotter, the ring will expand, and you never want the ring ends to butt into each other because it'll destroy the cylinder walls and make a big mess. Prematurely wear out your engine and actually cause quite a bit of damage. So Howard did the number 1 ring, and now he's doing the number 2 ring, compression ring. And it's a little bit tight, so we use this ring end grinder to set the clearance. You could use a file, but this makes it really easy to do a precise job. You sit in the vise and use this abrasive wheel, and you can actually count the revolutions. When you're first getting a feel for this, you just want to do it a little bit at a time, like that. And then grind on it. And then what you do is you put it back and measure the change in gap. Now this is a feel thing. When you're first learning, you just want to do the smallest amount. When you get more experience, you'll have more of a feel on how much to grind. Different ring materials grind differently too. Usually the steel top ring will need more grinding than the bottom, just because it's kind of a harder material. But it's a matter of feel. So if you're a beginner to this, just do a little bit at a time. Like you can always take out more, but you can't add it when you took out too much. Right, Howard?
Yeah.
So once you've got your correct clearance, it can leave a sharp edge with some burrs. So you use like a knife sharpening stone and you stone the edges. You don't want to go to town and take a lot of material off, but you just want to take out any burr that you might have raised. Like a burr can scratch the piston groove, or it can scratch your bores. So just knock that burr off and you're good to go. So we went over assembling the short block. Now it's assembling the head. Now Howard's mostly assembled this head, so you wouldn't have to watch the whole thing, but he's left the important parts off for one. The first thing is you just put the valve seals in. They just press down onto the valve guides, and then you just put the valves in, and there isn't a whole lot to do. You know, like one of the things we do is that we really inspect the valve job, and particularly making sure the 45 degree is nice and concentric and doesn't have any pits or anything weird. Sometimes the machine shop messes this up, and the 45 is not concentric and really thin in some places. So in this case, we may lap the valve by hand a little bit or go back to the machine shop and yell at them. But our machine shop does a good job all the time, but we still inspect it. So the head is mostly assembled, and I guess Howard, he's going to be working on this cylinder. So what are you going to do next? Put the seals in?
Before that, spring sheet.
Oh, okay, yeah. We're running double valve springs, so the spring seat has to go in first because the valve seal is bigger than the hole in the seat. So that just drops in like that. Then put a little like lubricant on and drop them in. Same thing with the valve seal. These are from valve seals are Super Tech, and they're made out of Viton, which is a real high temp elastomer. It's probably better than the stock stuff. They just mostly press in place. Next, lubricate the valve stems and just kind of push them smoothly through there so the keeper grooves don't kill on the valve seal too much.
This is your camera here. When you're talking to it.
All right, so the valves are in now. Howard's seen the valve seals now with like the end of a extension, and the valves just push through there. Now it's time to put the springs on, since they're interference type springs. Give them a dip in lubricant. We use regular mineral oil. Sometimes for the lobe of the cam, we'll use some of that assembly lube, the red stuff, but for most things we just use regular motor oil. So you can see the interference fit of the springs is pretty tight, and Howard pushes it in there. Then he gets the retainer and the keepers, gets the keepers lined up in the retainer. And positions it on top of the valve. Then we use a valve spring compressor. It's like a giant C-clamp with a socket with a hole cut out in it, so you could manipulate the keepers once everything gets in the right position.
Good movement, I guess. Mess this up.
So you slip the retainers into the keeper grooves on one valve. Now it's the other one. You basically tighten it down, and you can kind of watch them, and you'll see when they snap down in place. When you're doing this, you want to take your time and make sure the inner and outer springs are resting on the retainer correctly, and the keepers are lined up and in the groove. Now, some guys recommend hitting all the valves with like the end of a hammer to make sure that the keepers are seated, but I don't know. I don't really think that's necessary because it's super obvious when you look at everything whether it's seated or correctly or not. Right, Howard, or do you do that?
No,
You just eyeball it, right?
yes.
Now Howard's installing the lost motion plungers for the VTEC system. They just go into holes in the head that they're there. That kind of holds up the one lobe while VTEC's being engaged. And now it's time for the rocker shaft. So this is motor oil, right, Howard?
Yes.
And is that an assembly lube or is that motor oil too?
Just the motor oil.
Oh, okay. So you position the rocker shaft and slide it through the rockers. So there's two for the low RPM lobe and one for the high RPM lobes. Now there's the VTEC activation plunger, and you got to make sure that that's in the proper place and it's nice and free. It's pretty obvious, like if it slips out of its bore, the rockers won't line up. So there you go, the rockers are all lined up. Lost motion assembly is all properly engaged. You can see it has tension and it moves freely. So we're going to repeat that on all the other rockers on the intake side of the engine. The exhaust side is identical. So next you install the retainer that keeps the shaft from sliding out, and it also helps line up the oil holes and introduces oil into the shaft. So now all the rocker assembly and all the valves and springs and retainers and keepers are in place. Now it's time to install the cams. So you can place the cams in the head. One of the things when you install cams, it's very important not to torque them off center because you'll actually break the cam pretty easily. So you have to be very careful in this step. We use Redline assembly lube when it comes to the cam. There's a lot of pressure on the cam lobe itself, and during braking it's important to not get any scuffing. So Howard's applying the braking lube to the lobes. He also applies braking lube to the cam followers and the cam journals in the head. Now in the pinch I've used oil before, but I don't really recommend that. Really recommend you use a proper braking lube for the cams because it's critical. But having to change cams at the track and things like that where I didn't have everything, I've used oil. Nothing bad happened, but still, you know, why risk anything with a new motor? So once again, applying the lube to the cam journals in the head and the rubbing pads on the rocker arms, and lube up the cam. And when you assemble the cams for the first time, like for number one cylinder, you want the intake and exhaust lobes to be facing away from each other, kind of like in the V. You can see that right there. That gets you sort of in the ballpark. Howard's applying lube to the journals on the cam caps. A small amount of sealant to the cam cap that actually goes outside the engine because the valve cover gasket doesn't really seal around there. This is a common thing to do with many different engines. We typically use Permatex Gray or Honda Bond or Yamaha Bond. It's all kind of the same stuff. We don't use regular silicone. So just a little bit of sealant right where it goes past the valve cover. You don't want to go to town and use a whole bunch. It can squish out and break off and start migrating around the engine and causing problems, clogging up oil passages and things like that. So you just want to barely put a little skin of it on there. What's kind of cool about Hondas is they have these top plates which maybe make braking the cam a little bit harder. It helps kind of even out the tension between all the caps. Some engines like Nissan that just have the individual caps, it's super easy to bust the cam. But you still got to be careful even with a Honda. So Howard's going to slowly start torquing the cam caps down. He's going to do it in an X pattern from the inside out, and just a little bit at a time in many steps. Just minimize the stress on the camshafts. They are made out of like cast iron or something, and they're actually pretty brittle. They're hardened for long life, which makes them even more brittle. I mean, it's not like impossible, but you just got to be careful. And I've seen many people break their cams. So just remember, inside out in an X pattern. A bunch of small steps. So once all the caps are snugged down, it's time to torque them. Use the torque to get them up to the final torque spec, but now all the caps are all bottomed out on the head, and you don't have to worry about stressing out the cam. So it's the same thing. You start in an X pattern and go from the inside out. The outer bolts are torqued down with the inch-pound torque wrench. They're small bolts, so they don't have to be that tight. There you go, the head's together. So we assembled the head completely just so you could see what it was like, but in reality, the head has to be partially assembled on the block to get at some of the head bolts. But so we're going to reset and put the head down. So when you install the head, the first thing you want to do is make sure the deck surfaces are really clean and dry. Like Howard just used some brake cleaner and a shop rag and got the deck surfaces absolutely dry. Next thing you want to do is make sure that you have all the dowels in your block in position and ready to go. Then you're actually ready to put the head on. So I guess you're going to put the studs in first. Like everything else, we use the ARP lubricant. You can kind of see it on the ends of the studs and the threads. It's really important to get an accurate torque reading, and we only use ARP. It's kind of like the industry standard. And most rods and whatever, the lubricant specified is ARP. Next, the head gasket's placed. It's a good idea to inspect the gasket first, make sure it's not damaged. MLS gaskets could possibly get kinked or creased. Make sure you have the right part number and it's not hanging into the bores or anything. Just a quick look. Now it's time to place the head. You just want to make sure the head comes straight down and seats on the block and the dowel pins. You don't want to move the head around on the head gasket and potentially damage it. So once the all the nuts and the washers are in, you have to use like ARP precision ground hardened washers to get the proper torque. You put the nuts in. Now Howard's snugging everything down, going in the X pattern, starting from the middle outward. so if you're using studs like ARP, you torque it in 3 steps generally, and you do it in the X pattern from the middle outward. Now, if you're using stock torque to yield bolts like from the factory, what you would probably do is torque it in 3 steps to the final torque, and you do the last stage using angular torque. So you'll have a guideline on what angle to make it. So Howard's gradually working up to the first stage of torque, starting in the middle, working out in an X pattern. Okay, now the head's installed, and we're going to put all the valve train stuff on that we showed you step by step. So we finished putting together the engine's bottom end. We covered all the tricky parts, the stuff that maybe isn't so obvious. So now we assembled the front cover and everything. I mean, that's pretty straightforward, and we installed the oil pump and the water pump. But we're now going to do the cam timing. Cam timing and degreeing in the cams is something that a lot of engine builders totally skip. They just set everything up to the stock timing marks and send it. But this is a big reason why a lot of cars maybe don't run as good as they should. A lot of this is because when you have performance cams, they need to be set at a different lobe center than the stock cams. And there's like tolerance creep, like if you surface the head, surface the block, little variances in machining and the cams, the gears, and the whole lash up, your cam timing can be off as much as 6 or 7 degrees. And that much can make the engine run really soggy and not perform like it should. So we're going to teach you how to do the cam timing. Now you should do this on every motor, even if you're running the stock cams, as long as you have the cam specs. Now every set of performance cams that you buy has the cam specs on the card that comes with the cams. And what we're going to do is we're going to be setting the lobe centers of these cams. On these particular Kelford cams, we use the low RPM lobe of the VTEC because the high RPM lobe can't be engaged without oil pressure. And those lobe centers are 104 degrees on the intake and 106 on the exhaust. So Howard's going to show how that's done. So the first thing, Howard's going to line up all the timing marks to the stock position. He's going to install the timing belt. Then he's going to put a dial indicator on the valve and the degree wheel on the crank, and then we're going to start. So go for it, Howard. So just to get things close, we're going to get number 1 cylinder on top dead center. Then we're going to install the belt and tension it and make sure all the stock timing marks are lined up. This is going to get you close. So once the belt is on, we're going to put the harmonic balancer on. Now Howard's putting the degree wheel on the front of the crank. So now that the degree wheel's on, Howard bends up an indicator for top dead center. We used a piece of welding rod. So we use that to indicate TDC. Right now the crank is at TDC using the stock timing mark, but this timing mark is so we can actually degree the cam in. So to hold the dial indicator, Howard puts this plate so the magnetic base of the dial indicator could go on there. And Howard's going to confirm that top dead center is correct by putting the tip of the dial indicator down into number 1 spark plug hole. So Howard's going to roughly find TDC by moving the crank back and forth and looking at the dial indicator. Then he's going to back up a few degrees and then write the amount of lift that the dial indicator makes and what degree it's on. Then he's going to turn in one direction and find that lift point on the other side of TDC. Then he's going to add the two numbers, the two crank degree numbers, and divide by 2, and that'll give the actual top dead center location. You use this method because it's really hard to exactly figure out where the needle reverses. So the given lift, you find where it is on one side of top dead center, move in one direction through top dead center, and find the lift on the other side. Add the 2 degree numbers you get, divide by 2, and that'll actually give you your TDC location. So once Howard figures that out, he'll adjust the pointer to indicate true TDC. So now Howard's figuring out the top center of the exhaust lobe. So what he's doing is puts the dial indicator on the valve. You never want to put it on the lobe, but on the valve, because a lot of motors that have followers have asymmetrically ground lobes to make symmetrical valve motion. So you always want to do it on the valve. So as you can see, Howard's doing about what he did on the to find the crank top dead center. Like he finds close to the maximum amount of lift, then he backs up, finds a consistent lift height, then he rotates the engine in the direction of rotation and finds that on the other side of max lift. Then he gets the 2 degrees and he adds them together and then divides by 2 to find the actual lobe center. So what's our exhaust center?
Right now it's a 1025.
So it's 1025 right now, and it's actually supposed to be at 106. So to correct it, Howard's going to use the AEM adjustable timing gear, and he's going to move it to correct the lobe center. Now, if this cam was just installed like that, it would really not perform like how it should. I mean, that's way off. And that's what a lot of amateur engine builders don't get right, is they don't get these numbers right. So after Howard adjusted the cam, now he's going to go back and do the same thing. So you rotate the engine in the direction of rotation, find a lift point on one side of the lobe, write the degree down, and then turn past the point of maximum lift till you reach your measuring lift point on the other side. Write that degree down, add together and divide by 2, and that'll be your lobe center. Now you want to always go in one direction while you're doing this, because it takes the whole ash of the valve train and everything into consideration. So don't reverse directions while you're in the middle of doing this. Always go in the direction of engine rotation. So Howard adjusted the cam, and where are you at now, Howard?
125.
Okay, a little bit too much. So you got to go back a little. I can't stress how important this step is and how many people ignore it. Having your cam off by 3.5 degrees is quite a bit. Now you're
10675.
okay, we're almost there. So Howard backs up, finds the lift point where he wants to measure the degrees, checks the degree on the degree wheel, and keeps rotating till he passes maximum lift and finds that point again. He notes the degree. He adds the 2 numbers. And divides by 2. 106.2, I think that's good enough. What do you think, Howard?
I think so.
Yeah, like 0.2 of a degree isn't going to make that much of a difference. Now we're going to move to the intake side of the engine. So number 1 cylinder, put the dial indicator on the low speed VTEC lobe on the valve, and we're going to go again. We're going to find TDC roughly. Then he's going to pick a valve lift point. He's going to note the crankshaft degrees. Then he's going to go in the same direction, the direction of engine rotation. Find that lift point on the other side of max lift. And then you'll have the 2 numbers. Divide by 2. And 91 lobe center, so we're way off. So it's supposed to be at 104. So now we're going to repeat the process. Find that lift point. Go through the zone of max valve lift. Find that lift point on the other side. Note the degree on both points. And then do the math. 102. Okay, now we're at 102. We're getting pretty close. So we're at 104.5. Do another small adjustment. So 104.25, I'd say that's pretty close. Once you've set your lobe centers, then it's best to spin the engine around and double check your work to make sure that everything is right. There's the lash in the belt and things like that, and you know it's good to take one last look before you send it. So Howard's going to go all over again for like a quick check. So the belt has a little bit of give, and the engine has some tolerance in the bearings and the cam, and it all moves around a little bit. So it's good to spin the engine all the way around and double check your work. So first, Howard finds TDC. You roughly find it by looking at the dial indicator, then back up and then turn in the direction of rotation. Stop at some point right before TDC. Note the degree. Pass TDC, stop at the same lift point. Note the degree. Add the 2 numbers up, divide by 2, and that's your TDC. And TDC was correct. Now you're going to check your cam top centers. First, we're going to check double check the exhaust side. So that's supposed to be at 106 degrees. So Howard's going to go around there, reset everything. So after everything's settled, it's about half a degree off, so we're going to make a small adjustment. This is totally normal, especially with all new parts. So that's how you set the cam timing. Now these are the factory specs. What actually works best for your engine may vary a little bit, but that really needs to be set on the dyno. Generally when you're on the dyno, what you'll do is try to advance the intake cam a little bit at a time till your power falls off. It could be set right, but depending on the combination of intake manifold intake and a few other things, and your header could be a little different. Try advancing first. If advancing doesn't help, try retarding a couple degrees at a time, see if that helps. Once you find your best power curve and all that with the intake, move to the exhaust. And the exhaust usually isn't as sensitive, but it's pretty much a lot to do with how your header and exhaust system is. So I would start by retarding your exhaust cam, a couple degrees at a time. And if that doesn't help, try advancing just a little bit. But usually your exhaust cam is not as sensitive. But as you can see, if we had just put the cams in and used the factory timing marks, the cam timing would be off quite a bit on a motor like this that's maybe about 10 horsepower. So not having proper cam timing is a reason that a lot of home builders, their engines don't run good, and that's why we check it on every one of our motors. So this is about all the hard parts with assembling a B-Series engine, but we take the same care with any kind of engine. So give us a like, subscribe, go to MotoIQ.com, check out our articles, check out our web store, and hopefully let us know if you like this assembly content, and we'll give you more.